Okay, now we move on to properties of colors. So the colors that we perceive, right, it has its own property. That means a theory that is actually related to colors, on how colors behave. For example, if let's say we have one perception that's saying that, okay, if let's say I'm seeing a blue colored chair, and if I go, if I'm sitting in a room and I'm seeing a blue colored chair, then when I switch off the light, I should see the blue color to be slightly darker. Okay, darker blue. But in reality, it is not. Okay, you will still see that blue color as the same blue color, even though the environment has actually become darker. Okay, it has its own properties. So we have, since we are learning optometric sciences, right? So we're going to look into slightly deeper on the properties of colors based on the research that it was conducted that many years ago. Okay, so we're going to look at one by one. Okay, so the first law or the first property of color is actually by this Grassmann's law of metameres. Okay, metameres means two colors look similar, but then the constitution of the color is different. For example, okay, if you get a coffee, okay, from two different shops, for example, one is the Costa Coffee coffee, and also another cup from Starbucks. Okay, although they are both look the same. Okay, for example, if you buy a black coffee from both and you get like a black coffee, but the black coffee of Starbucks would taste a bit more different than Costa Coffee, although they look the same color. Okay, because the portion of the sugar that is added, or the portion of the amount of coffee that is actually mixed to the coffee cup would be different, although the amount is the same. Okay, so that is metameres. They look the same. Okay, we perceive it to be same color, but the combination of colors to produce that outcome is different. Okay, and these metameres have a certain properties, okay, which we're going to discuss. So based on this Grassmann, right, he's a researcher, he said that this Grassmann, a guy, mentioned that when there are two colors which are metameres, okay, they have three properties. Okay, so what are the properties would be? Okay, so the first one is additive property. Okay, additive property means, okay, okay, for example, one cup of coffee, as the example that I've given, is a mixture of A and B, while another cup of coffee is C and D. So it's the same, they look the same color. So if you look at here, it looks like a peach color here. Okay, so according to this Grassmann, he said that if let's say I add in, okay, C, okay, another color to the, sorry, if I add one additional color into this mixture, right? Okay, this is color mixture of A light and B light, while this is C light and D light. If let's say I mix up another extra light to this and this, the similar color, okay, both of them will actually, produce the same color. That means if let's say I mix, okay, light X and light X to here, it will produce green color, which will still look similar for both, although the foundation of the colors are different. So that is one properties of color, okay, based on Grassmann's research. Second one is scalar property. So scalar property means you have A mixture of B, C mixture of C. Okay, so this could be like 1 liter, and this one is also 1 liter. So they look like, this brownish color. If let's say I add on another 2 liter, okay, mixture of A and B to this, and then I increase the volume to another 2 liters, okay, the color would slightly change, okay, maybe it become pinkish, okay, but even if I increase for the other one, okay, which is the metamere of the first one, okay, which looks similar. The color also changed as the output of this one. Okay, so that is the another properties of colors. So when you increase the volume of the color, okay, it become, it changed to a different color, become more intense or become more lighter, but the outcome is the same for the two colors. And another one is associative. Okay, so if you see A and B, okay, this is the one combination produce the peach color, and C and D, it produce the peach color similar. Okay, and then it was found that, okay, when you mix another three colors, okay, it produces a green. Okay, and then we have original green also. Okay, so this is a mixture that produces green, and this is originally green. So this is already a metamer, and this is another metamer, but this metamer will be mixed to this one, and this green color will be mixed to this. And after the combination of these two, it will still produce the same color. Okay, so that is associative properties of color. Okay, as long as the output color is the same, when you mix to the metamers, the original metamers, it will still produce the same color. So that is the Grassmann's law. Okay. Next, we move on to color labels. Another property of color labels is how do you actually, label the colors. Okay, it helps in distinguishing between different items, conveying information, and enhancing visual appeal. Because we need, this color label so that when I say green, you know that it is green. If I say it is blue, then you know it is blue. Why? Because we're able to identify the colors according to the label that is already prefixed. Okay, so but there are ways of actually, identifying colors. Okay, so we look at this slide. So based on this, okay, so there are three ways of actually, defining a color or labeling a color. Okay, scientifically, yeah, I'm talking about scientifically, how do we actually label the colors? Okay, what I say like red, green, and blue is the layman way of actually, labeling the colors. But in the research world or in the science world or in the medical world, we need to have like a proper way of labeling the colors. And you as an optometrist, you have to know how to label it. So if let's say I'm talking to you in the lab, using these terms, then you should know what am I talking about. Okay, so we have the same language. Okay, so there are three ways to actually do this. One is hue, saturation, and brightness. Okay, these are the three ways of actually classifying or labeling the color. Okay, hue means is the if let's say using a layman term, it is the name of the colors. Okay, this is hue. Red, yellow, blue, green, red, all that are the hues, the colors, okay, of the light. Next one is the fullness of purity or color. How saturated is the color or how impure is the color. Okay, so that is the saturation. And the third label would be the brightness, how bright and how light is the color. So these are the terms that we use in medical to label the colors. Okay, so if let's say hue, right? Okay, physical dimension means how do we measure that? Okay, if let's say hue, it is based on the wavelength, longer wavelength, shorter wavelength. So that is the how we differentiate the hue. Saturation will be both the wavelength and the colorimetric purity, the purity of the color. Okay, while the brightness will be the radiance. Okay, of the color, that is actually, the measurement of radiance, okay, determines the brightness of the colors. So the first one is Grassmann law, the second one is color label, and the third one will be the wavelength discrimination. Okay, so wavelength discrimination, okay, it's the ability of the visual system to distinguish between different wavelengths of light. Okay, if let's say I give you two colors, right? Okay, if let's say you can say that A is different from B. So that is the ability to discriminate the colors. That means your brain can process the wavelength that is actually given to you, and then it is sensitive in the brain to actually perceive the colors to be different. Okay, but when you look at the the visible spectrum, from 400 nanometer to 700 nanometer, are they the same for all the wavelengths? For example, if let's say I give you 400 nanometer and 410 nanometer, okay, because it is differ by 10 nanometer, I expect you to be able to see there are two different colors. Okay, so but although it is 10 nanometer, it doesn't mean that you will be able to differentiate it. Okay, because at different point in the visible spectrum, they are at certain range that your eye are not sensitive enough to actually detect the small changes, okay, that differ by 10 nanometer or 5 nanometer. Okay, so we're going to look at that. Okay, so this is the graph. Okay, the graph, the x-axis, it is the wavelength of the light. Okay, from visible spectrum 400 nanometer to about 700 nanometer. And the y-axis is the smallest detectable difference in wavelength that can be distinguished. Okay, so that means if let's say I give you a color at about 300 nanometer. Okay, if let's say I give a 300 nanometer and I give you 301 nanometer, for example. Okay, sorry, 400 nanometer and 401 nanometer. You might be able to tell me that they are two different colors. Okay, but if let's say I give you around 480 to 481, okay, you might say that these two colors are the same, because at this wavelength, the colors are not, okay, the cones are not able to detect them as two different colors, or the brain not able to differentiate at two different colors. Okay, so this graph explains that. Okay, so the higher sensitivity is sorry, I was wrong. Okay, if let's say I give you about 400 nanometer and 401 nanometer, you might not able to differentiate them. You need them to be in different range, then only able to differentiate it. The same applies for if let's say I give a longer wavelength one. So if let's say I give you about 650 to 6, if let's say I give one color 650, another one 655. Okay, you might not able to actually differentiate them. You might say that both the colors look alike. But if let's say I give about 480 and 481, even though the difference is by 1 nanometer, you're still able to discriminate them and tell that these are two different colors, okay, or two different shades, for example. So that is what meant by this wavelength discrimination research. They say that higher sensitivity of colors is in the mediums spectrum, which is between this 500 to 600 nanometer. So we have a better discrimination. Even with a small range of nanometers also, we will be able to differentiate them as two different shades or two different colors. While those who are actually about 400 or 400 nanometer and also 700 nanometer, they have a poorer discrimination. Although we give them as about 10 nanometers difference, also they might perceive them as the same colors. So that is wavelength discrimination. So better discrimination, human eye has better wavelength discrimination, as I say 500 and 600. So the overlapping responses of these cones allow for finer distinction between the wavelength. Okay, because there is overlap between the medium wavelength cones and the longer wavelength cones. So the one that is sensitive to longer and the medium, they're overlapping in this range. Okay, so when they are actually working together, the sensitivity capability is better. So that's why they're able to do it. Okay, because we have shorter, medium, and long. Okay, so what happens in this 500 to 600 nanometer? Okay, the capability of discrimination is overlapping between this medium wavelength cone and also longer wavelength cone. So when they work together, they have better discrimination. While this poorer discrimination, which is the one, 450 nanometer and the 650 to 700 nanometer. They solely depends on their own cone, the long and the short one, because there are fewer cones, so they actually performs, slightly poorer compared to the medium wavelength one. Okay. And next one, okay, the first one is Grassmann's law. The second one is color label. And then the third one is wavelength discrimination. So the fourth property of color would be Basel-Bouquet phenomenon. Okay. So Basel-Bouquet phenomenon is, okay, perceived shift in hue of a color when its intensity or brightness changes. For example, if let's say I have a blue color, okay, I increase the intensity and brightness of the color. When I increase the intensity, for example, okay, the blue, when I increase the blue's intensity, I would expect it to become actually, when it is like the darkest blue, it will be more like a black color. Okay. Typically, as the intensity increases, the hue of the color appears to shift towards, blue or, darker color. Conversely, as intensity decreases, the hue shift towards yellow color. For example, if let's say I have any color, okay, for example, a blue color, if I increase the intensity, I would expect them to actually, become slightly like a blackish color. But in reality, when you increase, how much increase the intensity of the blue color, you will still see blue, you will not see some other colors. But you're expecting that when I increase the intensity of the blue color, it might look like a blackish color. So that's our humans' perception. But in reality, it doesn't happen that way. How much blue that you add in also, it will still look like a blue color. Okay, because of this Basel-Bouquet phenomenon. Okay, so despite the increase in intensity, the hue of the colors remains unchanged. Okay, based on the experience, they show that how much red that you put also, how much green that you put also, it will never actually change to another color. Okay, so it will stay in that color. Okay, so this means that as the brightness of the color increases, it doesn't shift towards another color. Instead, it maintains its original blue color. Okay, so when the intensity of color is increased, it essentially making it brighter or vibrant without altering the underlying hue. Okay, so when you shift the intensity, when you increase or decrease, it might look brighter or lighter only, but it will never ever change to another color. And the last one, last property of color would be the color constancy. So the first one is Grassmann's law. Second one is color label is another property. The third property was the wavelength discrimination. The fourth property is the Basel-Bouquet phenomenon. And the last one would be the color constancy. So this is the example that I have given you just now. Okay. The color constancy means, okay, so as I mentioned earlier, phenomenon where the perceived color of an object remains relatively constant under varying light condition, whether it's bright, dark, it's in the morning, at night, or is it during twilight. Any time a blue will still look like a blue. A red color pen will always look red. Okay. Even though the wavelength of light hitting the eyes may change, humans still perceive the color of objects as the same. Okay, why? Okay, why do, when I switch off the light, the color still looks blue when I expect it to be darker blue? Okay, because the visual system adapts to changes in lighting conditions to maintain color constancy. So we have a visual system which is very particular that you turn off the light, you turn on the light, you dim the light, you make it lighter, I will still adapt the wavelength as same. Okay, it will never change my perception. So that is a concept that we have. So that is a factor why, okay, because visual system in our bodies build up that way. Okay, it is not getting influenced by the it is not getting influenced by the extra illumination or the out illumination. Okay, the color of an object is influenced by the colors of surrounding objects. Okay, so the color of an object is influenced by the colors of surrounding objects. Brain takes into account the context of an object when perceiving its color. So what it is meant by this, point is, okay, the color of the object is actually, influenced by the, surrounding objects. If let's say they are toys like red, green, blue, and yellow toys on a table, okay. So by looking at other toys, we know that this is our blue color, even if I change the illumination. If let's say I'm targeting on a red color, even if after I turn off the light, I will still seeing that, as a red color, because, comparing to other colors at the surrounding. And also perception of color is influenced by memory and expectation. We have been seeing this for many, many years. So our perception is already fixed. That if I see a red color, I know it's a red color. Even if you turn off the light, also I will see a red color. Okay, so it is the perception because of the memory and expectation that we have already in our brain. So that information is already kind of stick into the brain. So that is a reason why we don't actually see colors differently at different lighting. Okay, thank you.